And now, join us for an insightful exploration into virtual motorcycle prototyping with Enrico Picotti, postdoc from the University of Padova, alongside Masatsugu Nishimura, Assistant Chief Engineer at Honda Racing, and Mattia Bruschetta, Assistant Professor. This presentation unveils the development of an advanced virtual rider capable of controlling motorcycles during complex maneuvers. Discover how nonlinear model predictive control and generic algorithms optimize performance within virtual environments.
Thank you, everyone. Good morning. I'm Enrico Picotti, and I will present the work that we have done at the University of Padua, together with the Professor Mattia Bruschetta, and on the Racing Corporation for some part of the work, and of course with the VI grade products that we used. So we will talk about virtual motorcycle riding, in particular with the tool that is nonlinear model predictive control. That is an advanced technique that we have used for many years now to actually ride the motorcycle in the virtual simulation environment. So I don't think I will really need to convince you that a virtual rider is useful, but still this is the beginning of the story. So we know the importance of virtual prototyping tools, and we know the importance of human-like virtual riders in particular. In literature, we have different examples of NPC applied to this task. That is quite tough. It is quite tough for different reasons. First of all, because the rider is necessary, so it's needed. We cannot have open-loop tests. The motorcycle is unstable. And then we know that the rider presence of the motorcycle influences the dynamics of the motorcycle itself. And actually, the rider and the passenger and the load mass can be comparable with the motorcycle mass. And the stiffness of the rider, in particular on the steering, can actually change the modes, the vibration modes of the motorcycle, etc. And then, finally, the riding style is really significant in how the motorcycle will behave once on the real road. So the leaning behavior, it's really affecting the dynamics. Oversteering, for example, at the exit of the corner, etc. So what we did is apply this technique, nonlinear model predictive control, on riding a motorcycle in simulation. First, we worked on a model of the motorcycle that could run runtime within the control structure. So we built an analytical model that is based on Lagrangian formulation, and we used the steering, throttle, brake, and lateral position on the saddle of the rider as the control inputs for our model. So the rider, in particular, the moving rider, is represented as a point of mass that can move laterally on the saddle. And in this way, we could also enforce the rider movement, a specific rider movement that we want to model, because we know that from reality, this is what happens. Then we moved on, and we applied the learning-based strategies on the nonlinear model predictive control technique. So we developed a tuning strategy that actually tunes the controller in order to obtain the best performance. We will go through the details, and a learning dynamics strategy that actually helps us in getting a better model within our controller. So let's start with, I will present actually 3 papers that we have presented in the last years. So let's start with the first paper that presents the design of the NMPC controller. So how does NMPC work? So just a very brief idea of what an NMPC is. So it's a control strategy that is based on three main characteristics. First of all, we have a model, top left there. So it's nonlinear model predictive control. So we have a nonlinear model inside. Then we have a cost function there on the left, bottom left. And the cost function is our task. So it should define our task. What we want to do, we define a function that expresses what we want to do. And then, based on our model and our cost function, we can predict how our model will behave in the future and minimize our cost function on this prediction. That is actually the algorithm. So out of this, we get the inputs that we want for the real, or actually the simulated motorcycle in this case. So we have the steering and the movement and throttle and brake. So what we did is this motorcycle rider model. We have a sliding plane that, as I said, has a moving mass that is representing the rider. So we have here the center of mass of the rider that can move laterally. You can see the image at the bottom right. Then we have longitudinal forces that are linear. Then we have Passeca lateral forces, drag force, dynamic load transfer, and gyroscopic effects. And just to be clear, this is what we have inside our control strategy. So this then will be applied to the VI-BikeRealTime model, simulation model, that will be our reality, okay? So within our controller, we have this analytical model, and what we want to do is actually to track a given trajectory and velocity profiles. So we have the heading lateral error, we have the velocity, the cost function, and then we keep all the other velocities to regularize our system, because we don't want the bike to slide too fast laterally, yaw velocity too high, and roll velocity is too high, okay? So as you can see, we have a lot of cost function terms, and we will see afterwards that it's not easy to decide how to actually penalize each part of this cost function. So what we obtained, we compared with a static rider controller that we developed before. So you can see here on the bottom left, we have the moving rider profile. So you can see that the rider is actually moving as we expect, so it's leaning into the curve. You can see that we reach over 50 degrees of roll angles. And what is really interesting is that just adding a lateral movement of the rider of around 15 centimeters, the center of mass of the rider, we can actually travel the curves with much higher speed. And you can see the profiles there on the right. And actually, all the curves are traveled at much higher velocity, just because we were able to put this information that is the moving rider, okay? Okay, so this was the first result that we had in 2021. Then, as I was saying, we have the problem of tuning those controllers. This is an advanced technique that is actually has a lot of cost terms, and then has a lot of parameters to be tuned. So what we have developed is a tuning strategy for this advanced controller. And how we did that, so we actually get back to our NMPC structure. What we add is a data-driven cost function tuning. So we use the simulation to actually get the tuning, the best tuning of our controller. So how we did that? So we use this genetic algorithm that is not nominated sorting genetic algorithm. How it works? We start at the beginning with a random initial population. So we try some parameters, actually, randomly. And from that, we get different. From there, we can mix all these parameters in some para-random way and get some new candidates that we want to try. There, then, we simulate our system, so the control system, and we simulate the whole lab. From there, we get some results. So we want to minimize something, right? So that's the idea. And we will see in the next slide what we are going to minimize. But the important thing is that we get the results, so we evaluate the cost function, and we sort our results. So we get, with different cost functions, the problem is how to sort the results if we have, for example, 2 cost functions. If we have 1 cost function, it's pretty easy, right? We just sort them. If we have 2 cost functions, it's kind of not obvious. So what we can do is to use this non-dominated sorting. That means that we build what is called a Pareto front. It's this kind of figure here. So what you will have is a sorting for the 2 functions, and you will have an edge here. So you will have a kind of barrier, and the solution of this barrier are non-dominated. That means that they cannot be better on both the cost functions that you are considering. So they could be better on one side, but they cannot be better for both of them. So this is actually the edge of your cost function considered together, okay? So then, once you have sorted this, you can go on with the loop there, okay? So what we are optimizing from one side, of course, lap time. We want to go fast. So to do that, we just use lap time as a cost function. And if we do not end the simulation, because we know that some of the configurations of the controller could lead to like the motorbike falling down and this kind of stuff, we use a trick just to prefer the ones that are going more farther away, so closer to the end. And then we optimize the sensitivity with respect to the tuning parameters. What does this mean? This means that we are looking at how changing one of the parameters will change the lap time. So if I change one parameter and the lap time is changing drastically, this means that we are in a very not robust situation, because just a very slight changing in the parameters will completely change the effect, the results. And this works also for changing in the environment, in the motorcycle. So if I'm in a point where I change anything and I will fall down, that is not what we really want. So we want to go fast, but at the same time, we want to be sure that we can manage to change something within our simulation. So from one side, lap time, from the other side, robustness of our configuration. And our idea was these two will actually be on the contrary side of our Pareto. So that is actually what happened. So you can see the results in terms of the optimization. You can see at the beginning, we have a lot of the red dots. We have a lot of configuration that will go out of the track, so we do not want this. And we have actually a kind of random disposition of our results. Then, after 10th generation, we can start to see something, building something like a Pareto. After 50 generations, we will get something that is very similar to the theoretical Pareto. And we can actually see that we span 1.5 seconds in the lap time. So we actually get a quite high range in our lap time. And now, in a moment, I will show you. We have also a difference, high difference in the sensitivity of our simulations. And what does this mean? This means that we are, as we were discussing, very close to what is unstable. So we are very, very fast. But you can see here on the bottom the steering control for the very fast configuration. You can see it has really nasty vibrations. It's very very high frequency vibration on that. And you can imagine that as soon as you change anything with this behavior, you will fall down, okay? So you can see we have the robust one that is very smooth, it's quite slow, and we have the very fast. But the interesting thing is that on the Pareto, you can actually choose whatever you want there. So you can try different situations. Okay, so last thing I want to show you is the very last paper that we presented that we had in January 2024. So what we did this time is we put the data-driven strategy on the model side. So the model, we have seen the model before. It was an analytical model. We have classical X dot OD model in terms of first-order derivative. We have our system state and input. So we have a nominal dynamics, but we knew that that was not enough. So what we want to do is to augment our model with something, with the parts that we do not know, that we are not able to actually get analytically. So we build a gray box dynamics model where we have the nominal one, that is the one I presented at the beginning, and the augmentation. We use Gaussian processes to get this augmented model, and if someone is interested, we can discuss that later. These are function approximators that can estimate actually a function value, okay? And what we obtained is quite impressive. You can see here in the video the nominal physics-based controller and the gray box model controller. Let me see if this... can you please start the video? No way. We don't have the codec for this. That's fun. Maybe we can show it later. I don't know. Okay, you will have to deal with the figures instead of the video. I'm so sorry. What we get is that the nominal physics-based model is the red one, while the gray box model controller is depicted in blue. What we can see is that we actually reduce the tracking errors by 75%. The angular that is not shown is reduced by 60%, and look at the velocity profile error is reduced by 70%. Okay, so we actually got a very high reduction in terms of tracking errors, because we actually were able to get a better model within our controller. And the solver time, so the time required by the algorithm to run, is around 75% more, but it's still 6.6 milliseconds. So we are still able to run real time at 100 Hertz. Okay, so just to conclude the presentation, we have seen that a human-like rider model is fundamental, and I think you all knew that, for having good results in simulations. So we can use learning-based strategies to get better results, and implement better virtual rider. But still, it's very hard to get a realistic virtual rider by algorithms. Okay? So future possibilities could be to acquire data from real or simulated real rider, so from a simulator or from the real world. We have the video? Okay, let's show the video then. Okay, so the red one is the nominal and the blue one is the gray box. Okay, you can see that the nominal one was not really able to completely track, while the blue one is nearly perfectly aligned on the DRD on the trajectory. And just to be clear, this was a profile that was at around 90% of the maximum performance of a motorcycle. Okay. Thank you. Okay, so I will very quickly conclude. So could be a future possibility to use real data. So we have seen that data-driven strategies could be used. So why not use real data from a real rider or from a simulator? And so we can actually adapt our virtual rider to the reality. That's all. Thank you for the attention.